Picture this. You're in the final round of a coding interview for your dream job. The interviewer gives you a classic problem, to-sum. Given an array of integers, nums, and a target, check if any two numbers in the array sum up to that target. You feel a sense of relief. You know this one. So you confidently start typing out a solution you know works. Simple enough, right? The code is clean. It's correct. The interviewer nods slowly and then asks the one question that separates junior developers from senior engineers. What is the time complexity of this solution? Answering this question is not a nice to have. It is the absolute gateway to a deeper technical discussion and a non-negotiable impact sound skill for any top engineering role. This video is your 90 minutes masterclass to conquer that question. You're going to master the entire toolkit. First, Big O notation, the fundamental language of efficiency. Then, recurrence relations, the math that models recursion, like T of n equals 2T of n over 2 plus n. We'll also cover the recursion tree method, a visual technique to solve any recurrence. And finally, the master theorem, a powerful shortcut. My promise is simple. You will master complex recursive functions, confidently derive their time complexity, and articulate your analysis like a seasoned engineer. Back to our interview scenario. You've just presented your solution. It's correct, it works, and you're feeling good. But then they ask that critical follow-up question. This is a solid start, but can you do better? What they're really asking is, can you write a more efficient algorithm? The measure of better in these situations almost always comes down to time complexity. So let's look at solution 1, the brute force approach. The idea here is simple. For every number, we check it against every other number. We can see the code here. Def 2_sum_brute_force. Inside, we've got our counter for operations, and then the main part, a for I loop with a nested for j loop inside it. That's where we do the check. If nums of I plus nums of j equals target. For our small input of 6 numbers, this takes 15 operations. Seems fine, right? But what if the list had 10,000 numbers? We'd be looking at roughly 50 million operations. The work grows quadratically. We call this O of n squared. So how can we find a pair without that nasty nested loop? The key is to use a hash set to remember the numbers we've already seen. Here's the logic for the one-pass solution. For each number x, you ask a very simple question. Is my perfect match target minus x already in the set of numbers I've seen? If the answer is yes, you've found a pair. You're done. If the answer is no, you just add x to the set and move right along. Simple and elegant. This leads us to solution 2, the optimized O of n approach. Let's look at the code. Def 2_sum_optimized. We create an empty set called scene, and then we have just one loop. For each number, we calculate the potential underscore match, which is just target minus num. Then we check if that potential match is in our scene set. If it is, we return true. If not, we add the current number to the set. So much cleaner. Let's trace the optimized solution together step by step to see how this works. Our numbers are 3, 5, 2, 8, 11, 7, and the target is 10. First, the current number is 3. The potential match we're looking for is 10 minus 3, which is 7. Our scene set is currently empty. Is 7 in our set? No. So we add 3 to the set. Next up is 5. The potential match is 10 minus 5, which is 5. Our scene set now has a 3 in it. Is 5 in our set? Nope, so we add 5. Now for the number 2. The potential match is 10 minus 2, which is 8. The scene set contains 3 and 5. Is 8 in the set? Still no, so we add 2. And here's where the magic happens. Our current number is 8. The potential match is 10 minus 8, which is 2. Our scene set has 3, 5, and 2. Is 2 in our set? Yes, it is! We found it! Return true. The optimized algorithm found the answer in just 4 operations. With 10,000 elements, it would take at most 10,000 operations. This linear growth is called O of n. Now here's the wow moment. This is why this is a game changer. Look at this table. With an input size of 100, the O of n solution is 50 times faster. When we get to 10,000 elements, it's 5,000 times faster. And for 1 million items, the O of n solution is 500,000 times faster. It's just staggering. You can see it right here in this graph of linear versus quadratic growth. The green line, that's our O of n. It's linear, predictable. That red line shooting for the sky, that's O of n squared. The difference is unbelievable. The optimized O of n solution isn't just a little better. It's in a completely different league. An O of n squared algorithm on 1 million items might take minutes, maybe even hours. The O of n solution on 1 million items? A fraction of a second. This is the entire point of time complexity analysis. We need a predictable way to describe growth rate to compare algorithms without having to run them. And that formal language is Big O notation. Let's dive in. Big O notation is the language of algorithmic growth. It answers one critical question, and that question is this. As my input, which we'll call n, gets huge, what is the worst-case growth rate of my algorithm? It's a way of classifying code not by seconds or minutes, but by how it scales. That's the key word right there, scales. We're going to focus on the practical rules that will get you 99% of the way there in any coding interview. There are really only 2 rules you need to master for most problems. Let's start with rule 1. Drop the constants. Big O doesn't care about precision. It cares about the shape of the growth curve. So something like O of 2n, well, that just simplifies down to O of n. Or maybe O of n divided by 3. Same thing, it becomes O of n. And what about O of 500? Well, that's just a flat number. It doesn't change with n, so it simplifies to O of 1. We call that constant time. Let's look at this in some code. We have a function called printItemsTwice that takes in a list of items. This first loop runs n times, so that's O of n. Simple enough. Then we have this second loop that also runs n times. That's another O of n. The total work is n plus n, which equals 2n. But what's the rule? Drop the constants. So the final complexity is just O of n. Okay, on to rule 2. Keep the most dominant term. If your algorithm has different parts, like one that takes n steps and another that takes n squared steps, the faster growing term is the only one that matters at scale. Think about it. If n is 1 million, then n is, well, 1 million. But n squared? That's 1 trillion. The n squared term completely dwarfs the n term. So O of n squared plus n simplifies to O of n squared. What about O of 2 to the n plus n cubed? That 2 to the n is a monster. It simplifies to O of 2 to the n. And O of n plus log n? The n term grows faster, so it simplifies to O of n. Here's this in code. A function called mixed operations. First, we get the length of the items, n. This first part, the single for loop, we already know that's O of n. But look at this next part. We have a nested loop, a loop inside of a loop. This part is O of n squared. So the total work is O of n plus n squared. But again, what's the rule? Keep the dominant term. The final complexity is O of n squared. This brings us to the growth rate hierarchy. This is your cheat sheet. You need to know this chart by heart. This is your roadmap for writing efficient code. Look at this chart, you can see the different complexities compared. At the bottom, you have O of 1, then O of log n, O of n, O of n log n, O of n squared, and way up at the top, O of 2 to the n. Let's walk through this table together, step by step. At the very top, we have O of 1. That's called constant time. An example is just accessing an array element, like ARR bracket I. The performance? Instant. Next is O of log n. That's logarithmic. Think binary search. The performance is excellent. Then we have O of n, or linear. Looping through an array once. That's great performance. O of n log n. We call that log linear. Efficient sorting algorithms like merge sort fall here. Performance is good. Now things start to slow down. O of n squared is quadratic. Those nested loops we saw. Performance is just okay. Then we get to O of 2 to the n. Exponential. This is where brute force recursive solutions often land. The performance is terrible. And finally, O of n factorial. Factorial. Like a brute force traveling salesperson solution. The performance is astronomically bad. This is the practical language of growth. With these rules and this hierarchy, you can start analyzing basic algorithms. We've learned the practical rules of the road for Big O. And for 99% of interviews, let's be honest, that's all you need. But what about for that final 1%? For the moments when an interviewer really pushes you and asks, "Can you prove that?" Now, the goal here isn't to be a mathematician. Don't worry. It's to understand the one core idea that makes all those rules work. Asymptotic analysis. Let's frame this with a core idea. A horse race. Imagine two algorithms. Algorithm A, its exact runtime is f of n equals n squared. And then there's algorithm B. Its exact runtime is f of n equals 100n plus 500. Okay, let's start the race with a short sprint where n is just 10. For algorithm A, f of 10 is 10 squared, which is 100. Pretty fast. But for algorithm B, f of 10 is 100 times 10 plus 500, which is 1,500. So for this short race, algorithm A wins. You see, algorithm B has a huge startup cost, and these big constants that make it look slow at first. But this is just noise. It doesn't reveal the algorithm's true nature. But now, let's run a marathon. Let's set n to 1 million. Algorithm A, f of 10 to the 6th power is 10 to the 6th squared. That's 10 to the 12th power. 1 trillion operations. Now look at algorithm B. Its runtime is approximately 100 times 10 to the 6th, which is 10 to the 8th power, or 100 million. It wins by a landslide. As n gets huge, that n squared term completely dominates everything else. Asymptotic analysis is the formal study of this long-term behavior. Okay, deep breath. Here comes the formal definition of big O. We say f of n equals O of g of n if there exist positive constants c and n0 such that 0 is less than or equal to f of n, which is less than or equal to c times g of n, for all n greater than or equal to n0. Okay, I know that looks terrifying. Let's break it down. F of n is your algorithm's actual messy runtime. You know, like 3n squared plus 10n plus 5. G of n is your clean, simple approximation. That's the n squared part. C is a constant wiggle room factor. It lets us scale g of n to be an upper bound. And n0 is a threshold input size. It just means we only care about what happens after n gets big. So, in plain English, f of n is O of g of n if we can find some constant c that makes c times g of n an upper bound for f of n once n gets big enough. Okay, now that we have the definition, let's use this to prove the two rules we learned. Example 1. Proving drop the constants. Let's prove that f of n equals 3n is O of n. Our goal is to find constants c and n0 such that 3n is less than or equal to c times n for all n greater than or equal to n0. Let's look at that inequality again. 3n is less than or equal to c times n. This is easy. Let's just pick a constant c that's bigger than 3. Let's choose c equals 4. The inequality becomes 3n is less than or equal to 4n. Now when is that true? Well, it's true for all n greater than or equal to 1. So we can just pick n0 equals 1. And that's it. Proof complete. We found constants c equals 4 and n0 equals 1. The definition holds. Now for example 2, proving keep the dominant term. Let's prove that f of n equals n squared plus 5n is O of n squared. Our goal is to find c and n0 such that n squared plus 5n is less than or equal to c times n squared for all n greater than or equal to n0. Okay, this one looks a little trickier. Let's try to make the right side bigger. What if we pick c equals 2? Let's see what happens. The inequality becomes n squared plus 5n is less than or equal to 2n squared. Okay, let's simplify this. We can subtract n squared from both sides. That leaves us with 5n is less than or equal to n squared. Now we can divide by n, since we know n is positive. And we get 5 is less than or equal to n. Proof complete. The inequality holds for all n greater than or equal to 5. So we found our constants. C equals 2 and n0 equals 5. This is why the rules work. They aren't just arbitrary guidelines we follow. They are just quick, practical applications of this formal mathematical definition. We've laid the mathematical foundation. We've even proven why the rules of Big O work. Now, it's time to move from theory to practice. Before we can even think about analyzing complex recursion, we must be able to instantly recognize its building blocks. This is a rapid bootcamp to make that analysis second nature. Let's go. First up, the building block. O of 1, also known as constant time. So what is O of 1? An operation is O of 1 if it takes a constant amount of time, no matter how big the input is. It's a single fixed step. How do you spot it instantly? Look for these things. Basic math operations like plus, minus, multiply, or divide. Assigning a variable. And this is a big one. Accessing an element in an array or a hash map. Like with my_array bracket 5. Let's look at an O of 1 example. Check out this function, def get first element, which takes in items. The first line says first equals items bracket 0. That's just one O of 1 operation. The next line is print first. That's another O of 1 operation. So the total complexity is O of 1 plus O of 1, which is O of 2. And of course, we drop the constant, so it just simplifies to O of 1. Simple as that. Next up, the workhorse, O of n, or linear time. What is O of n? This is when the runtime grows in a straight, linear line directly proportional to the size of the input n. If you double the input, you roughly double the time. It's that simple. How do you spot it instantly? This is the dead giveaway, a single for loop that iterates through all n elements of a collection. Let's see an example. Here's a function, def find sum, which takes nums. The first line, total equals 0, is just an O of 1 operation. Then we hit the loop, for num in nums. This loop runs n times, where n is the length of nums. The work inside the loop, total plus equals num, is just O of 1. And the final return statement is also O of 1, so the total work is O of 1. Plus n times O of 1, plus another O of 1. The n term completely dominates, so the final complexity is O of n. And now, the bottleneck, O of n squared, quadratic time. What is O of n squared? Here, the runtime grows proportionally to the square of the input size. This is where things can start to get slow. Fast. And how do you spot it instantly? It's almost always nested loops, where both the inner and the outer loop iterate up to n. Look at this O of n squared example, a function called createPairs. The first two lines, creating an empty list and getting the length, are both O of 1. But then we see it. The outer loop runs n times, and for each of those iterations, the inner loop also runs n times. The work inside is a simple append, which is O of 1. So the total complexity is n times O of 1. The final complexity is O of n squared. All right, practice set number 1. Time for a pop quiz. Question 1. What's the big O? Look at this code. Def check middle of items. It gets the length, finds the middle index with floor division, and then checks if the item at that index is hello. Pause the video right now and think about it. Okay, you ready? The answer is O of 1. Why? Because finding the length, doing a single division, and accessing an element by its index are all constant time operations. The runtime doesn't change one bit with the input size. Question 2. What's the big O? Here's a hint. Let n equal the length of list A and m equal the length of list B. The function is countMatches. It has a loop inside another loop comparing items from each list. Pause the video. What's the big O? The answer is O of n times m. Why? Because the outer loop runs n times. And for each of those, the inner loop runs m times. Now if n and m were the same size, then it would simplify to O of n squared, but we have to be precise. Okay, final question 3. What's the big O? The function is process data. It has 2 parts. The first part is a single loop that prints each item. The second part is a nested loop that prints the indices. You know the drill. Pause and give it your best shot. The answer is O of n squared. Why? The total work is the first part, O of n, plus the second part, O of n squared. But remember our rule. We always keep the most dominant term. The n squared part grows so much faster that it completely defines the runtime for large inputs. The O of n part becomes totally insignificant. You've just crushed the basic training. Analyzing for loops and if statements is now second nature to you. But we're about to step into the real maze of recursion. How do you analyze the runtime of a function that calls itself? Its work isn't a simple loop. No, it's a branching chain of calls, a cascade of subproblems. To do this, we need to translate the logic of our recursive code into a powerful mathematical equation. This equation is called a recurrence relation. Learning to solve them is the key that unlocks all of recursion analysis. Our first case, the factorial function. Our mission is to find its big O complexity by proving it step by step. Look at this code for factorial of n. You've got your base case, which is the stopping condition, if n is less than or equal to 1, and then you have the recursive step, where the function calls itself. We'll use a simple, repeatable 3-step process. Define, expand, conquer. Step 1. Define the relation. First, let's call the runtime of factorial of n as t of n. Now look inside the function. What's the work being done in the current call? Well, there's one comparison, n is less than or equal to 1, and one multiplication, n times something. This is constant work. Let's just call it c, or O of 1. And what about the work from the recursive call? The call to factorial of n minus 1 takes time t of n minus 1. So let's put it all together. Here is our recurrence relation. T of n equals t of n minus 1 plus c. And our base case, when we stop, is t of 1 equals c. This formula is the mathematical soul of our code. Step 2. Expand the relation. We'll use what's called the substitution method. We're going to walk through this together. Start with our formula. T of n equals t of n minus 1 plus c. Now, what is t of n minus 1? Well, using our own formula, it's t of n minus 2 plus c. So let's substitute that in. That simplifies to t of n minus 2 plus 2c. Let's do it again. We substitute for t of n minus 2. That gives us t of n minus 3 plus c, plus the 2c we already had, which equals t of n minus 3 plus 3c. A crystal clear pattern is emerging. After k steps of this expansion, we're going to get t of n equals t of n minus k plus k times c. Step 3. Conquer the pattern. This expansion has to stop somewhere, right? It stops when we hit our base case, t of 1. This happens when n minus k equals 1. And if we solve for k, that means k equals n minus 1. Now, we just substitute this value of k back into our pattern. This simplifies to t of 1 plus n minus 1 times c. We know t of 1 is just c, so we get c plus nc minus c, which equals nc. The total work is just n multiplied by some constant c. Conclusion. The time complexity of factorial of n is O of n. Okay, let's try applying the process to binary search. Let's analyze this classic divide and conquer algorithm. Looking at the code, you can see the base case, then some constant work to find the middle, and then a recursive call on either the left half or the right half. So let's define the binary search recurrence. Binary search does constant work, which we'll call C, and then it calls itself on a problem half the size. So our recurrence relation is t of n equals t of n divided by 2 plus c. And the base case is still t of 1 equals c. Step 2. Expand the relation. We start with t of n equals t of n over 2 plus c. Substitute t of n over 2, that becomes t of n over 4 plus c, plus the original c. So we get t of n over 4 plus 2c. Let's do it one more time. Substitute t of n over 4, which gives t of n over 8 plus c, plus the 2c we already had. So we have t of n over 8 plus 3c. The pattern here is a little different. After k steps, the denominator is 2 to the power of k. So our general formula is t of n equals t of n divided by 2 to the k, plus k times c. Step 3. Conquer the pattern. Again, the recursion stops when the problem size is 1. So we set n divided by 2 to the k equal to 1. Now we solve for k. So n equals 2 to the power of k. To get k by itself, we take the logarithm. So k equals log base 2 of n. The number of steps k is the logarithm of n. That's the key. Now, substitute this k back into our pattern. T of n equals t of 1 plus log base 2 of n times c. And since t of 1 is just c, we get t of n equals c plus c times log base 2 of n. And for the final step, we drop the constants and any lower order terms. Conclusion. The time complexity of binary search is O of log n. The substitution method is great for simple recurrences. But what happens when recurrences get more complicated? Like t of n equals 2t of n divided by 2 plus n. That's a bit trickier, isn't it? For these, we need the recursion tree method. This is a super visual and intuitive way to solve these problems. Our first pattern we're going to master is the balanced tree. This pattern appears when the work done at every single level of the recursion is exactly the same. Keep that in your mind. Let's dive into our main example for the balanced tree. Imagine an algorithm that divides a problem of size n into 3 subproblems, each of size n divided by 3. And it does O of n work to combine them. The recurrence for this is T of n equals 3T of n divided by 3 plus n. Now, let's unleash our 4-step method on this thing. Here's our recurrence again. T of n equals 3T of n divided by 3 plus n. Step 1. Draw the tree. We're going to visualize this. At the very top, our root node has a cost of n for a problem of size n. This node then splits into 3 children. Each child works on a problem of size n over 3, so their cost is n over 3. And each of those children splits into 3 more, and so on. It branches out really fast. Alright, let's move to step 2. Calculate the work per level. This is where the magic really happens. At level 0, the top level, the work is just n. Simple enough. Now for level 1. We have 3 nodes and each is doing n divided by 3 work. So the total work is 3 times n over 3, which is just n again. Whoa. Okay, what about level 2? We have 9 nodes now and each one is doing n over 9 work. The total is 9 times n over 9, which is, again, just n. Do you see the pattern? It's happening again. The work at every single level is constant. It's always n. It doesn't decrease, it doesn't increase. It's perfectly balanced. This is the signature. This is the dead giveaway of a balanced tree. When you see this, you know what you're dealing with. Okay, on to step 3. Determine the tree height. The recursion has to stop somewhere, right? It stops when the problem size shrinks all the way down to 1. So at some level, let's call it k, the problem size is n divided by 3 to the power of k. We just set this equal to 1, so n over 3 to the k equals 1. A little algebra tells us n equals 3 to the power of k. To solve for k, we just take the logarithm base 3. So k, the height of our tree, is log base 3 of n. We're on the home stretch. Step 4. Sum the work across all levels. This is the easiest part. We know the work per level is n. We know the number of levels, or the height, is log base 3 of n. So the total work is just work per level times the number of levels. T of n equals n times log base 3 of n. Our conclusion, T of n is big O of n log n. Now, here's a crucial point for big O. Listen closely. The base of the logarithm doesn't matter. O of log base 3 of n is the same as log base 2, or natural log. We just write O of log n. So, to confirm this method works, and isn't just some magic trick, let's reanalyze binary search and see if we get the same O of log n that we got with the substitution method. Practice time. Binary search. The recurrence, if you remember, is T of n equals T of n divided by 2 plus 1. Steps 1 and 2. Draw the tree and calculate the work. This tree is, honestly, incredibly simple. It's not even a tree, it's more like a stick. Each node just has 1 child, and the work at every single level is just 1. Step 3. Determine the tree height. The problem size at level k is n divided by 2 to the power of k. We stop when this hits 1. So n over 2 to the k equals 1, which means k equals log base 2 of n. Exactly like we saw before. And now, the final step. Step 4. Sum the work. The work per level is 1. The number of levels is log base 2 of n. The total work is just 1 times log base 2 of n. The recursion tree confirms it. T of n equals O of log n. We got the exact same answer. This method is reliable, it's powerful, and I think you'll agree, it's much more intuitive than all that messy algebra. So far, we've seen examples where the work at each level of the recursion tree was the same. But what happens if the work at each level is not the same? What if that non-recursive work, that plus f of n part of the recurrence, is incredibly expensive? What if the initial call does a massive amount of work and the recursive calls do less and less and less? This leads us to our second major archetype, the root-heavy tree. All the computational cost is concentrated right at the top. For our main example of a root-heavy tree, let's consider an algorithm that does O of n squared work, then makes a single recursive call on a problem half the size. The recurrence is t of n equals t of n over 2 plus n squared. Alright, you know the drill. Let's run our 4-step analysis. Okay, we've got our recurrence. T of n equals t of n over 2 plus n squared. Step 1. Draw the tree. Now look at this diagram. The tree looks like a long, thin stick, and the cost absolutely plummets as you go down. The root node has a cost of n squared for a problem of size n. Its single child has a cost of n over 2 squared, which is n squared over 4. The next level is n squared over 16. It's shrinking fast. Step 2. Calculate work per level. This is pretty straightforward. Level 0, n squared. Level 1, n squared over 4. Level 2, n squared over 16. So at some level k, the work is n squared divided by 4 to the power of k. This is a geometrically decreasing series. The work is shrinking rapidly. This is a huge clue. Step 3. Determine the tree height. We've seen this a few times now. The problem size at level k is n divided by 2 to the power of k. We stop when n divided by 2 to the k equals 1, which means n equals 2 to the k. So the height k is just log base 2 of n. Simple enough. And now, step 4. Sum the work across all levels. The total work, t of n, is n squared plus n squared over 4 plus n squared over 16, and so on. Let's factor out that n squared term. T of n equals n squared times the series 1 plus 1/4 plus 1/16 plus, well, you get the idea. Now that series in the parentheses is a geometric series with a ratio of 1/4. The sum of an infinite geometric series is just 1 divided by 1 minus the ratio. So that's 1 divided by 1 minus 1/4, which is 4/3. So the total work is just t of n equals n squared times 4/3. Here is the key insight. The total work is just a constant multiple of the work at the root. In fact, that first n squared term accounts for 75% of the total work. The root level completely dominates the runtime. Our conclusion is simple. T of n is big O of n squared. Okay, let's do a practice problem to really nail this down. Analyze this. We have two subproblems, each 1/3 the size, and a massive O of n cubed amount of work at each step. So, t of n equals 2 times t of n over 3 plus n cubed. Let's test our intuition. Steps 1 and 2. Draw the tree and calculate the work. At level 0, the work is n cubed. Easy. At level 1, we have 2 nodes. Each one is doing work on a problem of size n over 3, so the work is n over 3 cubed. The total work for level 1 is 2 times n cubed over 27, which equals 2/27 times n cubed. Stop right there. The ratio of work between level 1 and level 0 is 2/27, which is much less than 1. The work is decreasing geometrically. We already know the answer. Steps 3 and 4, height and sum. Let's take the intuitive leap. The tree height is going to be k equals log base 3 of n. We know that. And because the work is geometrically decreasing, we know the sum is going to be dominated by the very first term. The root level's work, n cubed, provides a tight upper bound. We don't even need to do the full sum. Conclusion: T of n is O of n cubed. This root-heavy pattern gives us a powerful new heuristic. If the work at each level is geometrically decreasing, the total complexity is determined by the work at the root level. That's a shortcut you can use to solve these kinds of problems much, much faster. Now we complete the trifecta with the third and final major pattern. What happens when the recursion branches out so aggressively, spawning so many children, that the amount of work actually increases with every level you go down? This leads to a leaf-heavy tree, where the vast majority of the work is concentrated in the final, deepest level of the recursion, the leaves. All the action is at the very end. Let's look at our main example, the explosive recurrence. Imagine an algorithm that does O of n work, but then breaks the problem into 4 subproblems, each half the original size. The recurrence looks like this. T of n equals 4 times T of n over 2 plus n. This feels explosive. Let's prove what happens. Okay, main example. T of n equals 4 times T of n over 2 plus n. Step 1. Draw the tree. The branching factor here is huge. It just explodes outwards. At the top, we have a cost of n. Then it branches into 4 children, each of size n over 2. And then those 4 branch into 16 children. It's wild. Now for step 2. Calculate work per level. At level 0, the work is just n. Simple enough. At level 1, we have 4 nodes, each doing n over 2 work. The total is 4 times n over 2, which equals 2n. Okay, now for level 2, we have 16 nodes, each doing n over 4 work. The total is 16 times n over 4, which is 4n. Stop and look at that pattern. N, then 2n, then 4n. This is a geometrically increasing series. The work is doubling at every single level. On to step 3. Determine the tree height. The problem size at level k is n divided by 2 to the k. We stop when that equals 1, which means n equals 2 to the k. So, our height k is just log base 2 of n, same as before. Now, remember, for a geometrically decreasing series, the root-heavy one, the first term dominated. But for a geometrically increasing series, the exact opposite is true. The last term dominates the entire sum. This brings us to step 4. Sum the work, but let's just focus on the leaves. The runtime of this entire algorithm is determined by the work done at the leaf level. That's all that matters. So, how much work is that? It's the number of leaves times the work per leaf. Work per leaf is O of 1. We just need the number of leaves. The number of leaves equals the number of branches raised to the height. So that's 4 to the power of log base 2 of n. Okay, how do we simplify 4 to the log base 2 of n? This is the classic interview log trick. Let's walk through it together. 1. Rewrite 4 as 2 squared. So now we have 2 squared, all raised to the power of log base 2 of n. 2. Use the exponent rule that says a to the b to the c is a to the b times c. So we get 2 to the power of 2 times log base 2 of n. 3. Use the log power rule that lets us move that multiplier inside as an exponent. So now we have 2 to the power of log base 2 of n squared. And 4. Use the identity a to the log base a of b just equals b. The result is n squared. There are n squared leaves in this tree. The work at the final level is O of n squared. And because this last level dominates, it defines our complexity. Conclusion: T of n is O of n squared. You've just seen how the tree method can produce a clean polynomial result. Now let's see how it can derive something that looks truly complex, proving just how powerful this tool is. Let's do a practice problem, deriving a complex result. Consider this: 3 subproblems, each half the size, and O of n work at each step. That's T of n equals 3 times T of n over 2 plus n. Okay, step 1 and 2. Calculate work per level. Level 0, work is n. Level 1, 3 nodes, each doing n over 2 work. Total equals 3 times n over 2, which is 3 halves n. Level 2, 9 nodes, each doing n over 4 work. Total equals 9 times n over 4, which is 9/4 n. The work is being multiplied by 3 halves at each level. Since 3 halves is greater than 1, we know instantly this is a leaf-heavy tree. Now for steps 3 and 4, height and sum, focusing on the leaves. The height is determined by the size reduction, which is n over 2, so k still equals log base 2 of n. And since it's leaf-heavy, the complexity is just the number of leaves. So that's the number of branches, 3, raised to the height, log base 2 of n. 3 to the power of log base 2 of n. How do we simplify this? We use another crucial log identity. A to the log base b of c is equal to c to the log base b of a. You can swap the base and the argument. Let's apply it. 3 to the log base 2 of n becomes n to the log base 2 of 3. And that's it. That's our answer. Log base 2 of 3 is just a constant. It's approximately 1.58. Conclusion: T of n is O of n to the power of log base 2 of 3. With the recursion tree method, you didn't have to guess, you proved it. You can now analyze almost any divide and conquer recurrence by identifying if it's balanced, root-heavy, or leaf-heavy. You've done the hard work. You really have. You've battled through the recursion tree method, drawing all those nodes, meticulously calculating the work at each level, and then summing it all up. You've seen the 3 great patterns emerge: the root-heavy, the leaf-heavy, and the balanced tree. You have built the intuition from the ground up. You earned this. But what if there was a way to solve almost all of these divide and conquer recurrences in under 10 seconds? What if there was a way to do it with no drawing, no summing geometric series, just a simple, powerful formula? Welcome to your new superpower, the Master Theorem. It's the ultimate shortcut, the cheat code you've earned by understanding the fundamentals. Let's look at the formula. This is your recipe for answers. The Master Theorem is a direct recipe for solving recurrences that fit this exact form. T of n equals a times T of n over b plus f of n. Let's break that down. A is the number of subproblems, which is just the branches per node. B is the factor by which the input size is reduced. And f of n is the cost of the work done outside the recursive calls. In other words, the work per node. Think of this as a tug of war. The Master Theorem compares 2 opposing forces. First, you have the force of recursion. This is how fast the leaves grow. We measure this with the term n to the power of log base b of a. And opposing it is the force of local work. This is just the work at each node, which is f of n. Now here's the interesting part. We just need to see who wins this tug of war. Look at this table. We compare the growth of f of n to n to the power of c minus c critical, where c minus c critical is just log base b of a. There are three cases. Case 1. The recursion wins. This happens when f of n grows slower than n to the log base b of a. What does this remind you of? That's right, it's a leaf-heavy tree, and the shortcut answer is simply theta of n to the log base b of a. Case 2. It's a tie. This is when f of n grows at the same rate as n to the log base b of a. The intuition here is a balanced tree, and the answer is almost the same, but we multiply by a log n factor. Theta of n to the log base b of a times log n. Case 3. The local work wins. This happens when f of n grows faster than n to the log base b of a. This, of course, is our root-heavy tree, and the answer couldn't be simpler. It's just theta of f of n. This isn't magic. It's the formalization of the exact intuition you just spent the last 3 sections building. Let's see it in action, applying the formula from minutes to seconds. Example 1, merge sort. The recurrence is t of n equals 2t of n over 2 plus n. First, the parameters. A is 2, b is 2, and f of n is n. Next, the critical value. Log base b of a is log base 2 of 2, which is 1. Now compare. F of n, which is n, grows at the same rate as n to the power of 1. Conclusion? This is case 2. The answer is theta of n to the 1 times log n, or simply theta of n log n. Done in seconds. Example 2. Our leaf-heavy tree. The recurrence was t of n equals 4t of n over 2 plus n. Parameters. A is 4, b is 2, f of n is n. Critical value. Log base b of a is log base 2 of 4, which is 2. Compare. F of n, which is n, grows slower than n squared. Conclusion? This is case 1. Recursion wins. The answer is theta of n to the power of log base 2 of 4, which is theta of n squared. Example 3. Our root-heavy tree. T of n equals t of n over 2 plus n squared. Parameters. A is 1, b is 2, f of n is n squared. Critical value. Log base b of a is log base 2 of 1, which is 0. Compare. F of n, which is n squared, grows faster than n to the 0, which is just 1. Conclusion? This is case 3. Local work wins. The answer is theta of f of n, which is theta of n squared. What took us minutes of drawing and calculation now takes seconds. This is the power of the master theorem. Okay, let's do a rapid-fire round to master these patterns. Check out this table. We're going to walk through this together step by step. First row, t of n equals 8t of n over 2 plus n squared. Let's identify the parts. A is 8, b is 2, f of n is n squared. The critical value, c crit, is log base 2 of 8, which is 3. Now the comparison. Our f of n squared grows slower than n to our critical value n cubed. That's case 1. The answer is theta of n cubed. Second row. T of n equals t of n over 4 plus 1. A is 1, b is 4, f of n is 1. C crit is log base 4 of 1, which is 0. we compare 1 to n to the 0, which is also 1. That means it's case 2. The answer is theta of log n. Third row, t of n equals 2t of n over 2 plus n log n. A is 2, b is 2, secret is log base 2 of 2, which is 1. Now compare f of n in log n to n to the power of 1. Well, n log n grows faster. That's case 3. Local work wins. The answer is theta of f of n, which is theta of n log n. Fourth row, let's go faster. T of n equals 7 t of n over 2 plus n squared. A is 7, b is 2. The critical value, log base 2 of 7, is about 2.8. We compare n squared to n to the 2.8. N squared is slower. That's case 1 again. The answer is theta of n to the power of log base 2 of 7. Okay, last one. T of n equals t of n over 3 plus t of 2n over 3 plus n. Wait a second, the splits, n over 3 and 2n over 3, are unequal. This doesn't fit the formula. The master theorem does not apply here. The master theorem is your essential shortcut for interviews. It's incredibly fast, but as you just saw, it's not a silver bullet. Its power comes from a very strict condition. It only works for recurrences in the form t of n equals a times t of n over b plus f of n. This formula assumes your problem is broken into a subproblems of equal size. If they aren't equal, you have to go back to the recursion tree. We just saw that the master theorem has a pretty big limitation. It raises an important question. What happens when an algorithm divides the problem into chunks of unequal size? Let's look at the challenge of an unbalanced split. Imagine an algorithm does O of n work and then splits the problem into 2 subproblems. But this time, one is 1/3 the size and the other is 2/3 the size. The recurrence for this would be t of n equals t of n over 3 plus t of 2n over 3 plus n. Now here's the kicker. This recurrence cannot be solved by the master theorem. It just doesn't fit the required structure. There's no single value for b. So what do? We panic? We guess? When the shortcut fails, you go back to the fundamentals. You go back to the recursion tree method. This is where your true mastery is proven. Okay, let's solve this unbalanced split problem. Our recurrence is t of n equals t of n over 3 plus t of 2n over 3 plus n. Step 1. Draw the tree. As you can see on the screen, this tree isn't symmetrical. At the top, we have the root node with a cost of n. It splits into 2 children. The left child has a cost of n over 3, and the right child has a cost of 2n over 3. The tree is already lopsided. The next level down, the n over 3 node splits into n over 9 and 2n over 9. And the larger 2n over 3 node splits into 2n over 9 and 4n over 9. It's definitely not a balanced tree. So let's move to step 2. Calculate the work per level. You might think this will be messy, but let's do the math. At level 0, the work is just n. Simple enough. At level 1, the work is n over 3 plus 2n over 3. That equals 3n over 3, which is n. Huh. Okay. What about level 2? The work is n over 9 plus 2n over 9 plus another 2n over 9 plus 4n over 9. If you add all that up, you get 9n over 9, which is n again. Wait, did you see that?
Despite the completely unbalanced nature of the splits, the total work done at each full level is still n. How is this possible? It's because the fractions always sum to 1. 1/3 plus 2/3 equals 1. This is a critical insight. Alright, on to step 3. Determine the tree height. For a big O analysis, we care about the worst case. That means we need to find the longest possible path from the root to a leaf. The longest path will always follow the largest subproblem. So it's the path n to 2/3 n to 2/3 squared times n, all the way down to 1. We can set the size at level k to 1, which gives us the formula 2/3 to the power of k times n equals 1. Rearranging that, you get n equals 3/2 to the power of k. To solve for k, we just use a logarithm. The height k is log base 3/2 of n.
Now for the final step. Step 4. Sum the work across all levels. Let's put it all together. The work per level is roughly n. The number of levels, or the height, is log base 3/2 of n. So the total work is just the work per level times the number of levels. T of n is approximately n times log base 3/2 of n. And of course for big O, we drop the constant base of the logarithm. Which brings us to our conclusion. T of n is O of n log n. Stop and think about what we just proved. This is a profound result. Even if a divide and conquer algorithm splits work unevenly, like 1/3 and 2/3, the complexity remains O of n log n. It behaves just like a perfectly balanced algorithm. This is why algorithms like randomized quicksort are so effective. Even with bad pivots that create unbalanced partitions, its average case performance is still O of n log n. The master theorem is a fast car for a smooth highway. But the recursion tree is the all-terrain vehicle that can handle any problem you throw at it. Let's venture into some new territory. What happens when a function doesn't divide the problem? What if it just subtracts? This brings us to subtract and conquer recurrences. Here, a problem of size n makes a recursive call on a problem of size n-1, or maybe n-2. They reduce the problem by a constant amount, not a multiplicative factor. These recurrences create tall, skinny recursion trees. And I have to be very clear about this. The master theorem is completely useless here. It just doesn't apply. So what do? We must rely on our fundamental tool, the recursion tree. Let's dive into an example I call the exponential nightmare. Imagine an algorithm that does a tiny bit of constant work. We'll just call it 1. Then, it makes 2 recursive calls on a problem just one size smaller. The recurrence looks like this. T of n equals 2 times T of n minus 1 plus 1. Step 1. Draw the tree. At the very top, we have our initial problem. The cost is 1 and the size is n. This single node then spawns 2 children. Each of those has a cost of 1 and a size of n minus 1. Then, each of those children spawns 2 more. So now we have 4 nodes at the next level, each with a cost of 1 and a size of n minus 2. You can already see where this is going. Now for step 2, calculate the work per level. Let's look at this table. At level 0, there's 1 node and the work is 1. So the total work is 1, which is just 2 to the power of 0. At level 1, there are 2 nodes. each does 1 unit of work, so the total work is 2, which is 2 to the power of 1. At level 2, we have 4 nodes. 4 nodes times 1 unit of work is 4, which is 2 to the power of 2. There's a clear pattern here. At any given level k, there are 2 to the power of k nodes. The total work at that level is simply 2 to the power of k. Step 3. Determine the tree height. This is where things get really different from divide and conquer. The problem size only goes down by 1 each time. The path is n to n minus 1 to n minus 2, all the way down to 1. This takes n minus 1 steps. So, the height of the tree is O of n. So let's process this. We have an exponentially wide tree that is also linearly deep. This is a recipe for disaster. Alright, step 4. Sum the work across all levels. The total work, T of n, is the sum of the work at every level. That's 2 to the 0, plus 2 to the 1, plus 2 to the 2, all the way up to 2 to the power of n minus 1. This is a classic geometric series, and the sum of this series is 2 to the n minus 1 divided by 2 minus 1. That simplifies beautifully. T of n equals 2 to the power of n minus 1. So what's our conclusion? T of n is O of 2 to the n. This is catastrophically slow. For an input of n equals 60, this is more operations than there are atoms in the known universe. But does subtracting always lead to disaster? Let's change just one number and see what happens. Welcome to the polynomial case. What if we do O of n, work at each step, but we only make a single recursive call on a problem one size smaller? The recurrence now is T of n equals T of n minus 1 plus n. Let's analyze this one. Problem: T of n equals T of n minus 1 plus n. Steps 1 and 2. Draw the tree and find the work per level. Well, here's the thing. The tree is no longer a tree. It's just a simple chain. At level 0, the work is n. At level 1, the work is n minus 1. At level 2, the work is n minus 2. And this continues all the way down until the work is just 1. Now, for steps 3 and 4, height and sum. The height is still O of n, just like before, but the total work is completely different. T of n is n plus n minus 1 plus n minus 2 all the way down to 1. This is a simple arithmetic series, and the sum is n times n plus 1, all divided by 2. When we expand that, we get 0.5 n squared plus 0.5 n. Our conclusion: T of n is O of n squared. Look at what just happened. Let's put these side by side. T of n equals 2t of n minus 1 plus 1 resulted in O of 2 to the n. Exponential. But T of n equals 1 T of n minus 1 plus n resulted in O of n squared. Polynomial. This leads us to the critical insight for subtract and conquer recurrences. If you make more than one recursive call where a is greater than 1, the complexity is almost always exponential. But if you make exactly one recursive call where a equals 1, the complexity is almost always polynomial. And that single number makes all the difference in the world. We have one more algebraic shortcut to learn: the characteristic equation method. This method is specifically designed for linear homogeneous recurrences with constant coefficients. Like the Fibonacci sequence, T of n equals T of n minus 1 plus T of n minus 2. But when can we actually use this thing? 3 simple rules. First, it has to be linear, no crazy powers. Second, homogeneous, just the recursive terms, no extras. And third, constant coefficients, fixed numbers only. Let's test some examples. T of n equals T of n minus 1 plus 2 T of n minus 2. Yes, it's linear, homogeneous, and the coefficients 1 and 2 are constants. Perfect fit. T of n equals 3 T of n minus 1. Same deal, works great. T of n equals 4 T of n minus 2. Yep, same pattern. But here's where things get tricky. T of n equals T of n minus 1 plus n. Nope, that extra n term breaks the homogeneous rule. T of n equals T of n minus 1 times T of n minus 2. Not linear anymore, we're multiplying terms together. T of n equals 2 T of n over 2 plus n. That's divide and conquer territory, completely different beast. T of n equals n times T of n minus 1. The coefficient isn't constant, it's the variable n. Alright, the recipe itself is dead simple. Assume your solution looks like x to the n, solve for x, then pick the biggest one. 3 steps, done. Let's solve Fibonacci step by step. T of n equals T of n minus 1 plus T of n minus 2. Step 1. Assume T of n equals x to the n. Step 2. Substitute to get x to the n equals x to the n minus 1 plus x to the n minus 2. Divide by x to the n minus 2. X squared equals x plus 1. Characteristic equation. X squared minus x minus 1 equals 0. Using the quadratic formula, x equals 1 plus or minus square root of 5, all divided by 2. 2 roots. x1 equals 1 plus square root 5 over 2, approximately 1.618. That's the golden ratio, phi. x2 equals 1 minus square root 5 over 2, approximately negative 0.618. Step 3. Compare absolute values. 1.618 is greater than 0.618. Dominant root is phi. Conclusion. T of n equals O of phi to the n equals O of 1.618 to the n. The naive Fibonacci algorithm has exponential complexity. Let's practice with more examples. Look at this practice table. T of n equals T of n minus 1 plus 2T of n minus 2. Characteristic equation. X squared minus x minus 2 equals 0. Roots. X equals 2, x equals negative 1. Dominant root is 2. Big O, O of 2 to the n. T of n equals 4t of n minus 2. X squared minus 4 equals 0. Roots. X equals 2, x equals negative 2. Dominant is 2. Big O, O of 2 to the n. T of n equals 5t of n minus 1 minus 6t of n minus 2. X squared minus 5x plus 6 equals 0. Roots. X equals 2, x equals 3. Dominant is 3. Big O, O of 3 to the n. Ah, beautiful! The characteristic equation gives us instant answers for these linear recurrences. You've learned how the characteristic equation can solve recurrences like Fibonacci's in seconds. It really feels like a perfect system, a clean 3-step recipe. But there's a catch. A hidden trap. An edge case. One that will lead you to the wrong answer every time. This section is the pro-level detail. This is what separates the expert from the apprentice. We're going to master the special case of repeated roots. So let's dive into the scenario.
identical roots. Consider this recurrence relation. T of n equals 4t of n minus 1 minus 4t of n minus 2. Let's walk through the steps we know. First, the characteristic equation. That's x squared minus 4x plus 4 equals 0. Second step, find the roots. We can factor this, and it becomes x minus 2 times x minus 2 equals 0, or just x minus 2 squared equals 0. And here's the catch. We don't have two different roots. We have one root, x equals 2, that appears twice. It has a multiplicity of 2. So what now? This is where we need a new rule. The rule for repeated roots. When a root r has a multiplicity of k, it contributes k different terms to the solution. Each one is multiplied by an increasing power of n. You get c1 times r to the n, c2 times n times r to the n, c3 times n squared times r to the n, and so on, all the way up to ck times n to the power of k minus 1 times r to the n. The big O complexity will be determined by the most dominant of these new terms. Let's go back and solve our example. T of n equals 4t of n minus 1 minus 4t of n minus 2. We found one root, r equals 2, with multiplicity k equals 2. Now we apply the rule. The root contributes two terms, 2 to the n and n times 2 to the n. So the full solution is t of n equals c1 times 2 to the n plus c2 times n times 2 to the n. Now for the final step. Which is the dominant term? Which grows faster? 2 to the n or n times 2 to the n? The term with the extra n factor wins, of course. Our conclusion? T of n is O of n times 2 to the n. The repeated root added a linear n factor to the complexity. This is the entire trick. Now for a surprising example. The recurrence that collapses. I promise, this will make the concept stick in your mind forever. Look at this. T of n equals 2t of n minus 1 minus t of n minus 2. At first glance, this looks exponential. But let's trust our new method. Okay, step 1, the equation. X squared minus 2x plus 1 equals 0. That factors to x minus 1 squared equals 0. Step 2, the roots. We have one root, x equals 1, with a multiplicity of 2. Step 3, apply the rule. The terms are 1 to the n, and n times 1 to the n. Now let's simplify and find the dominant term. 1 to the n is just 1, and n times 1 to the n is just n. So the dominant term is simply n. Conclusion? T of n is O of n. This is a massive insight. A complex-looking recursive formula just collapsed into a simple linear runtime. All right, let's put it all together. Welcome to the practice table, final boss mode. We are going to walk through this entire process together, step by step. First row, the recurrence is t of n equals 6 t of n minus 1 minus 9 t of n minus 2. The characteristic equation is x squared minus 6x plus 9 equals 0. This factors to x minus 3 squared equals 0. So our root is x equals 3 with a multiplicity of 2. The dominant term will therefore be n times 3 to the n. And the big O? O of n times 3 to the n. Perfect. Now that we've done one, let's speed it up a bit. Second row, t of n equals 3 t of n minus 1 minus 3 t of n minus 2 plus t of n minus 3. The equation is x cubed minus 3x squared plus 3x minus 1 equals 0. This is actually x minus 1 cubed. So we have one root, x equals 1, with a multiplicity of 3. So the dominant term will be n squared times 1 to the n, which is just n squared. The big O is O of n squared. Final row, t of n equals 5t of n minus 1 minus 8t of n minus 2 plus 4t of n minus 3. The equation is x cubed minus 5x squared plus 8x minus 4 equals 0. Now this one factors into x minus 1 times x minus 2 squared. So our roots are x equals 1 and x equals 2 with a multiplicity of 2. The dominant root is 2, and because it's repeated, its dominant term is n times 2 to the n, which gives us a final big O of n times 2 to the n. And with that, your knowledge of the characteristic equation is complete. Your algebraic toolkit for recursion is now fully equipped. We've covered all the major analysis techniques, from the fundamental visual method of the recursion tree to the powerful algebraic shortcuts of the master theorem and the characteristic equation.
Let's go back to where we started this hour. You're in that coding interview. You've just written a brilliant, elegant, recursive solution. The interviewer leans in, looks at you, and asks that million-dollar question. What is the time complexity of this solution? But this time, something is different. There's no panic. No guessing. Instead, you feel a sense of calm, of control, because you're not just a coder anymore. You're an analyst. You have a systematic toolkit to build your answer from the ground up. You have the confidence to explain your reasoning with absolute precision. You have just mastered the single most important skill for analyzing complex algorithms. All right, let's do a quick recap of your analyst toolkit. In this hour, you have acquired a powerful set of tools. First up, Big O notation, the formal language to describe an algorithm's growth rate. Next, the recursion tree method, your fundamental, all-terrain vehicle for solving any recurrence. Then, the master theorem, your ultimate shortcut for those classic divide and conquer algorithms. And finally, the characteristic equation, your specialized recipe for linear recurrences like Fibonacci. So, how do you decide which one to use? Let's look at a unified strategy for analysis. When faced with a new recursive algorithm, follow this mental flowchart every single time. First, write the recurrence relation. What is t of n? Second, check for shortcuts. Does it look like a divide and conquer problem? Use the master theorem. Is it a linear homogeneous recurrence? Use the characteristic equation. Third, if no shortcut applies, your fundamental tool will always work. You default to the recursion tree. And now, for the grand finale. The one slide you need to screenshot. The ultimate interview cheat sheet. Memorize this table. This is your golden ticket for recursion analysis. The final step is up to you. Practice. Apply this framework again and again until it becomes an instinct. You've got this.